The CPUs that we use today to power just about all of our computing needs understand instructions that have to be given in very specific formats. These instruction sets are not static things and tend to see changes over time, usually to seek out performance increases that can come in the form of representing work in a more efficient manner. x86 is no stranger to this. The x86 instruction set traces its roots back to the 8086 CPU of the late 1970s, but it has been extended over and over again to meet changing demands for more memory and for more specific instructions to make certain things faster. Intel has recently published yet another extension to the x86 instruction set that's called APX. APX stands for Advanced Performance Extensions, and I'm going to be looking at what exactly Intel intends to do based on the architecture specification that they've published. APX deals with changing up x86's integer side. It tries to make those instructions more efficient. And the first thing that it tries to do in that respect is that it doubles the register count. Originally, x86 had 8 architectural registers. Registers are like defined variables that you can store values in and operate on, and they're the fastest sort of memory available to a CPU. If you can get values from registers, that's faster than being able to get them from the cache hierarchy, and if you have more of those values, then you will generally have to spill them to memory less often. So when AMD extended x86 to 64-bit, they saw, hey, there's actually a real gain from going from 8 registers to 16, and that's what they did, alongside extending the operand width to 64 bits. The second major change is that the bulk of integer instructions get what Intel calls a new data destination, NDD, field. As x86 stands right now, integer instructions generally take 2 sources and overwrite one of them with the result. APX lets you not overwrite one of those sources. And another notable change is that you can suppress flag updates. Unlike other instruction sets like ARM or RISC-V, which actually decides to not have status flags at all, most x86 integer instructions will set a set of bits to indicate certain things about the result. For example, it'll set a carry flag if you add 2 numbers, and then that results in an arithmetic carry out of the register width. So if that carries out, then you can do arbitrary precision arithmetic by chaining add with carries. So you can do 2 64-bit add of carries, and you can deal with 128-bit integers. There's also a 0 flag that indicates whether or not the result is 0, and a few others. But generally, you don't need those flags unless you're going to be doing a conditional branch, or if you're going to be dealing with really big numbers. So what Intel is going to do is, hey, say if you don't need to update those flags, if you're not going to use those flags, you can just tell the processor not to set them. Finally, APX adds a few additional instructions, and that simplifies certain tasks, and I'll take a look at that too. So first, let's start with the first thing on the list, which is adding more integer registers, and let's look at how exactly Intel did that. And to look at what Intel has done, we need to look at how x86 encodes instructions. First, you have a set of optional prefixes, so that's how an instruction starts, and we will come back to that later. After that, you have an opcode. You always have an opcode. That stands for an operation code. At first, it started off taking 1 byte, but then as you started adding more and more instructions, Intel used escape sequences, which meant, hey, so first you have your first byte of the opcode, so 1 byte. And you would normally look this up in the map to see what operation it corresponds to. But if you have a special value, if you go to a special, like, if this exactly matches in hexadecimal, F, or basically 4 ones at the lowest bits, then go to an alternate map, and so on. This can actually happen twice. Sorry for the bad drawing. In essence, that means your opcode can turn into something like anywhere from 1 to 3 bytes, because we just have so many more instructions now than we used to in the 1970s. Now, after your opcode, this is technically all you need to encode an instruction. There are a lot of opcodes. Well, there are some opcodes that basically tell the CPU not only what to do, but what to do it with. For example, the push and pop operations that manipulate the stack. Well, the register is actually specified by the opcode directly, and also implicitly mess with the ESP, the stack pointer register. But typically, the opcode alone usually says, okay, this is what to do. It's not going to tell you what to do it on. And so we have another byte called the mod rm byte. And this basically stands for mode, register, or memory. And this is split into 3 fields. So within this 8 bits, 2 bits are a mode field. That tells you what exactly the last field, the last 3 bits, will do. You have a register field in the middle, that's 3 bits. The RM field is 3 bits. And the important thing here is that these 2 essentially address registers, but they are only 3 bits. So that means there are 8 possible registers. If you do 2 to the third power, that's 8. So you now have two fields that you can deal with that you need to extend if you need more registers. But that's not it, because remember in the mod_rm field, you could actually set the mode register to say, hey, I'm going to address memory with this. So this could either be directly using the address in a register to access memory, or it can be like using this register plus a small immediate that you can put at the end. But you can also do more complex things with that. If you use a special value here, 100, which would be ESP, but if you can't actually directly specify ESP here, then you are saying, I am going to use an extra byte. That's called the scale index and base byte. And that lets you do really complex addressing. That basically lets you do array indexing. And x86 is not the only instruction set to do this. This is an incredibly useful capability. ARM can actually do something similar. But the important thing here is now this lets you specify a 3-bit register index and base. So it's basically letting you do this calculation. But now you potentially have 3 registers to address in a single instruction. For example, you can do like add, let's say register REX to, this is specifying memory destination. Let's say RBX is your base, plus 3, actually scratch that, that's 4 times, I don't know, so let's say RSI. So this basically goes into array pointed to by RBX, and it selects the RSI TH. So let's say RSI is 8, then it will select the 8th element. And since this is multiplied by 4, 4 is 32 bits. Close enough. And that will let you use one instruction to address an array without having to use another couple instructions to do this somewhere else. But in any case, you now have 3 registers to deal with. All of these have to be extended. So let's look at what exactly AMD has done. They were like, okay, we're not going to mess with all the existing logic in mod_rm and SIB. What we're going to do is we're going to add a prefix. So they call this the REX prefix. I'm pretty sure REX stands for R extension, and R is picked because they already used E and X. So the backstory is when x86 got extended to 16 bits, they changed the A register to AX. AX is A extended, so it went from 8 bits to 16 bits. When they went to 32 bits, they took AX and made that EAX, so that's extended A extended, and that's 32 bits. And then when AMD went to 64 bits, they were like, okay, what do we use? We're going to throw a dart at a dartboard. Okay, we hit the letter R, so we picked R. So R is now 64 bits. I guess that's what this means. Anyway, this REX prefix starts with a well-known bit pattern. Actually, this is 4. So the first upper nibble of this byte is 4. And if you see this in a prefix, you know it's the REX prefix. And the lower 4 bits are what's really fun. You have the W bit, which is pretty obvious. That stands for width. If it's 1, then you are playing with 64-bit registers and 64-bit operands. The other 3 extend your register fields. So there are 3 bits here. And just as we covered before, we needed to extend 3 fields, and that's exactly what these bits do. So one extends the mod_rm register field, one extends the index field in the SIB byte, and then you only need one more bit because remember our mod_rm's RM field has to have a special value to use SIB byte. So if you don't use SIB byte, then B extends the RM field. If not, it extends the base field in SIB. So just to give an example, okay, let's say I'm adding the value in RBX to R15, R here, so I'm operating on 64-bit stuff. So I set W to 1, and then in the registers I'm addressing, well, I need to, this is R15, right? I cannot possibly address this with 3 bits, so I will use this to extend the RM field. And there I'm able to address the last register, R15, so we're counting from 0, so 15 is the last register. All is good here. Now, what if you want to address 32 registers? And that's where APX comes in. They basically took the REX prefix and said, okay, we're going to make it bigger. And we're actually going to use all 8 bits in a byte. So we're going to use, this is now a 2-byte prefix. The first byte specifies that this is a REX2 prefix. This is actually D5 in hexadecimal. So if you see that, that's the start of a REX2 prefix. After that first byte that specifies this is a REX2 prefix, you now see that the low 4 bits are exactly the same thing as the REX prefix. We've already covered this. What's interesting is the upper 4 bits. And that's basically extending those register fields further. 3 of those bits are taking those 3 register fields and bringing them up from 4 bits to 5 bits, which is how you get the ability to address 32 registers. You also have a legacy map bin, and this one is primarily to offset the impact of having this and trying to keep instruction length down. Remember how you could like take the opcode and have an escape sequence to be like 0x, 0f, and then your opcode is actually in the next byte and you have to look that one up in the map? Well, now you can just set this bit to 1. 1 means look in map 2, and then you don't actually need this extra byte here, and you've just offset the overhead of having this extra 2-byte prefix by cutting off 1 byte from the opcode. So that's a cool trick. Here's an example of how this could work for extending the registers. Let's say I'm trying to extend the RM field to an address, well, the last register possible in a set of 32 registers. And let's say I'm doing a register-register operation. So this means if both mode bits are 1, that means I'm going to directly use this to address a register value, like not do an operation that takes a value from memory. We're going to do a register-to-register operation. So then we can combine the 3 fields in the REX2, the 2 fields in the REX2 prefix. These are the 3rd bit and the 4th bit, so counting from 0. So this is actually, if you're counting from 1, this is the 4th bit and this is the 5th bit. Combine those with the RM field, and then you get 5 bits. You can do exactly the same thing with the register field, with the R here, with these R fields, and again you get 5 bits to address registers with. And finally, if you're using a scale index space addressing, then you can extend the base field with the B field. Now this applies to the base field, not RM. And you can do the same thing with the index field. So now you can use R31, like you can do something like, hey, add R31. R30 is the base, I don't know. Okay, this should be a plus. R29 times 4. And you could use all 32 registers in all 3 of these fields. So that's pretty cool. But then Intel didn't actually stop there. We know that they have this new data destination, and if we go back, there's actually not enough fields anywhere to encode a 3rd register unless you use the trick of, doing this, change this to an LEA, and basically hack this into giving you some non-destructive operands, which is already done, but Intel wanted to make this a little more flexible. So they said, okay, we did this APX 512 thing. We actually have another prefix, the EVEX prefix. And we are going to apply that to integer instructions. So this is what the prefix normally looks like. This is the EVEX prefix. You have a well-known first byte, and then this is actually a 4-byte total prefix. So each of these is 8 bits or 1 byte. And you can start to see why op caches are becoming cool. You've already wasted 4 bytes on a prefix. You still need an opcode. You're probably going to use a mod RM field. You're going to end up with like, this is 6 bytes right here. And yeah, so op caches basically cut down to having to pull 6 bytes out of the instruction cache. It tries to alleviate those instruction cache bandwidth issues. But the important thing is, you already have a lot of register bits in here. Like, hey, look, this is actually another field for addressing an additional register. That's really convenient. You conveniently have also extended the mod RM register field here with 2 bits. These are actually inverted. Don't worry too much about that for now. But it basically means that a 1 here means 0 and vice versa. I don't know why I decided to invert it. And you also have the X and B bits. So you can either extend fields into SIB, or you can combine both of those together to extend the RM field, which is actually kind of cool. But in this case, we already have a lot of what we need to implement a non-destructive destination. And indeed, if you use, like AVX 512 uses this as an additional source, you could already do non-destructive AVX 512 operations. Like you can do v-add, so packed add of single precision values, and you can do zm0, pretend it's m1, zm, and you can add the values in these into this without overriding either ZMM1 or ZMM2, because you can specify one of those sources here instead of doing so in mod RM. And you basically have a non-destructive destination already. So Intel was like, we have the decoding hardware for this EVEX prefix. What can we do to implement this for integer instructions in the cheapest way possible? I don't know, why don't we just slap this EVEX prefix on integer instructions? And that's exactly what they did. So you can recognize some of these fields from the REX2 prefix. You have the index field extended in SIB. You have the base field extended here. Base can also be, remember, the RM field in mod RM. And you have R3 and R4, which extend the register field in mod RM. And you basically have everything that was in the REX prefix, except it was longer. Sorry, the REX2 prefix, but now you've used 2 extra bytes. Well, what does that give you? Well, it gives you this non-destructive destination. So now, hey, this is your destination now. If you're doing, like, say, a non-destructive add, you can now do this in APX. You can do R15, let's say, R12, R31. You can use the extra bits here to encode R31. You encode R15 in this extra field. And notice one difference here is this is actually the destination here. This is one of the sources in AVX 512. This is one of the destinations. And then you also have these extra bits to play with that they haven't used. If you look back at AVX 512, like, these do not make any sense for integer instructions. This is actually a field for mask register. And masking is useful in vector operations, so you can turn off lanes. This actually tells you if you set this high, it means you're dealing with 256-bit width. If you set this to 1, you're dealing with 512. And this is broadcast. None of these are used for integer instructions. And we're going to get back to that later. But first, let's just look at how exactly, like I mentioned before, here's a visual look at how you would encode R31. You would set all of these bits to 1. And you would have a 3 operand add. You can simply extend existing fields. And in the most complex form, you can have a non-destructive destination, and you can have a scale index-based complex addressing thing. And now you have specified 4 registers, all of which can come from any of 32 regs. So that's pretty cool. Now, what Intel actually did with those extra bits down here is that they added another form of this. Not going to go into details here, but they let you suppress the flags update. So normally, let's say every x86 add instruction, like the regular add instruction, subtract, whatever, they set flags. So you could do something pretty cool, like, let's not do add, let's do sub. REX1. So you can do subtract from REX, and if it's 0, you can immediately put a branch instruction right after. Jump if not equal to 0, back to something early in your loop. So that lets you really naturally implement some loops without having to have an extra compare instruction here. But normally, like if you're doing arithmetic operations, you're not going to need this, so it's useful to suppress this flags update. And then they added a few extra instructions on top of that. One of those is JMPABS. It stands for jump, absolute. So it's saying jump to a 64-bit absolute address. So you give your opcode, and then you encode a massive 64-bit immediate, which tells you the exact 64-bit address to jump to. It's pretty funny. So the thing about this is originally x86 instructions, at least the ones that exist right now, they jump based on where you are, and you tell how far away to jump, and you could only specify it with a 32-bit immediate. And by the way, this is a signed value. So what it basically meant was that, say, in memory, you are here, and you want to jump. Well, now your jump distance is limited to plus or minus 2 gigabytes. Sorry, that's plus minus 2 gigabytes. If you want to jump further away, you would have to either chain jumps, or you will probably load a 64-bit value into a register and then do an indirect jump. So say jump to the value in this register. Well, that would take another additional instruction to actually load that 64-bit value into a register, and then another jump instruction to actually go there. And this would simplify that task. And then you also added a batch of conditional instructions, like you have CMP SCC or CTest CC. These are basically taking your CMP and test instructions. And they are saying do these conditionally. So if some condition is true, then do them as usual. If not, just set the flags to a set of default values that they've provided. And what I think this is letting you do is handle really messy, like, chained short-circuited stuff. Like if A is not equal to null. Sorry, that was really bad. Then do this. So and then check this condition, and A, let's say A is a pointer to a struct, A dot S is equal to 1. Then do some stuff. Well, you actually do not want to do this because you would do illegal like null reference if you try to do this. So what you actually do in a programming language is this would short circuit. You would evaluate this condition, you would skip this, and this is letting you do this without having to like nest instructions and possibly jump over some invalid code if this condition was false. Similarly, I think this conditional move thing, they've also added a set of conditional moves to, like x86 already has conditional moves, but this is more convenient because you can suppress faults. And what that means is in the old days, or what we currently have right now, cmove would actually read both. It's basically more of a C select than a C move. So even if the condition is false, it could fault if the address it should have written to, that it would have written to if the condition were true, is actually invalid. So what this does is it suppresses that. It's a cool way to make something more efficient without having to, like, normally this is to avoid making a branch. Well, you would have to branch anyway if the address were invalid, and this lets you not do that. Okay, now that we know about what Intel is planning to change with APX, let's look at some of the effects of those changes and try to guess at what kind of impact they're going to have. The first and most notable change is just having more ISA registers, so we're going to start with that. And to cut things short, the impact is probably not going to be all that big. It's likely going to be really limited for a lot of reasons. The first is that we saw AMD's data before. Going from 8 to 16 registers actually reduced the number of functions that would require register spills by quite a bit. We do not see anywhere near the same gain when we go from 8 to 16. And in some cases, you basically had very few functions that would spill. So the potential for actually having an impact is already limited from that. And then if we focus on this very small minority of functions where we could have a benefit, well, the thing is CPUs today are not the CPUs of the early 2000s. We actually have a lot more transistors to do cool tricks with, and one of the tricks they did was to make store forwarding essentially free in terms of latency. What that means is that if you're spilling a register, you're likely to read that register back because you needed data in the registers. You were going to use it again soon. So you're likely to store it, and you're going to read it back soon after. Both the store and load are probably going to be in flight at the same time. And when that happens, the newest CPUs like AMD Zen 4, Zen 3, and Intel's Golden Cove can actually do this with zero latency. They can forward the data basically for free. So the only cost, really, is having 2 extra instructions. So move, let's say you store, move, you load back the register that you spilled, you do something in between. The latency of these 2 extra move instructions is basically going to be 0. This test here, what it's doing is putting a chain of these dependent stores and loads, like a load that depends on a prior store, just chaining them together so we can measure the latency. And what you're seeing is that when the addresses match, which is going to be the case for register spills, they both go through in the same cycle. This one is not really latency measurement. It just means that these 2 instructions together went through in the same cycle. They took one cycle. Now, if the addresses don't match, but the load is completely contained within the store, then you can get a forwarding latency of like 6 to 7 cycles. But that's not what you're going to do with register spills. So the net effect is you're paying these 2 instructions, you're increasing your instruction count if you have to spill, and that's pretty much it. Now, implementing more ISA registers is also not free because it's a little complicated. In modern CPUs, you do not directly address your register file. So those ISA registers that you're encoding with like 3, 4, or 5 bits, those do not directly index into the physical register file. You actually have a much bigger physical register file. So let's take Zen 4. You actually have 224 integer registers. And those are physically present on a CPU. What actually happens is when you have an instruction, let's say like add REX1, this is not actually indexing into any fixed value here. It gets renamed. So REX, let's say it becomes R1 for the purposes of this discussion. And then let's say you loaded a new value into REX from memory. I don't know why PowerPoint is being stupid. Let's say some memory location. That REX is now R2. So what the CPU is doing is keeping 2 values of REX in. So now if you play with REX again, what basically happens is this and this are recognized as independent. Because now you're looking at a destination register of, well, you're looking at source registers that are actually R1 and R2. They are different registers to the out-of-order execution engine. These 2 can go in parallel, they can overlap. You can even issue these two in the same cycle. So what you're actually doing when you're saying I can address more ISA registers is you are reserving more of this register file capacity to hold values that are going to be kept there and visible to the program. And at the same time, because your register file capacity, let's say you have the same capacity, that means you're keeping fewer in-flight values. You have fewer values available for this sort of renaming. So you are trading retired register file capacity for in-flight speculative register file capacity. This trade-off is likely to be beneficial if your register file is already so damn huge that it doesn't really matter if you're like taking a little bit extra, this is not to scale, to hold retired values, because you're not really losing that much before you have to stall the front end. You're not losing that much renaming capacity, that is, but you potentially are reducing the number of instructions required in certain functions. The other change Intel made is to use that EVEX prefix to do non-destructive destinations. That also decreases the instruction count, and that's even harder to gauge the impact of. We don't have that data from AMD from the early 2000s when they did their research. Again, I suspect it's going to apply to some cases, but those cases that it applies to, it's not going to be very significant. And that's because, let's say you do not have this feature of a non-destructive destination. Let's say I have a value in R15 that I want to add to another value, but I want to preserve it. So I'm going to simply copy R15 to another register, move the value to another register, and then add it. That's equivalent to doing a non-destructive 3-operand add. So at first this is like an extra instruction, right? But then this move, because of register renaming before, they put tricks into the renamer. So modern CPUs, let's say starting from Ivy Bridge and starting from I think Zen on AMD, this becomes zero latency. Because if you think about how register renaming works, what you do is when you take this instruction, it goes into the renamer, you have a register alias table that then maps your architectural registers into a physical register file. So when you do a simple register-register move like this, there's no need to actually take an execution pipe to copy a value from one register to another. They figured that, hey, we can just take two architectural registers and point them to the same entry in the physical register file. So the renamer simply manipulates a couple of pointers and says, okay, I'm done. This instruction actually finishes before it even enters the execution engine. It has 0 cycle latency. Now there's some complexity to this. Like once you do this, you have to now ref count this so you know when you can free it. Normally when you retire an instruction, you know that you can free a particular register right away. That's not necessarily the case when you pull these kind of tricks. But we have enough transistors. They did it. And the effect is that all this does is take up a little bit of core width. It does not add any latency, which is arguably more important. And it's likely to have really very little impact. But let's try to put some figures on how this non-destructive destination and how increasing your register count actually affects your instruction count in the end, because that seems to be the goal here. We have other instruction sets like ARM, IBM Power, like PPC, and MIPS, which is basically what long soon is. These have 32 registers, and they also have a non-destructive destination. So this 64-bit ARM already can do things like add R1, R2, R3, and not overwrite either of the sources. It can also address up to 32 registers, so you can do R31 already. What we can see is that in this pure integer workload, I'm using pure integer workload because if you use something like video encoding or like some SIMD thing, x86 is AVX, and then that completely modifies the picture is going to use like half as many instructions as any of these other instruction sets to get the job done, simply because it can do more with each instruction. But with this pure integer thing, you can see a difference at most of like, this is under 10%. So you've gotten a decrease of under 10% in terms of how many instructions you're executing. The effect is that x86 had to crunch through a few more instructions. I mean, it does right now. But then if you look at the actual performance, that tends to not matter so much. What then happens is that for the extra instructions it has to execute, Zen 2 here is basically getting more IPC and just totally offsetting that. And on top of that, it actually delivers the best compression performance of any CPU here, simply because it executes at a much higher clock speed. So this ends up going at like, what, something like 23 megabytes per second. By the way, I'm compressing just some fixed size file here because 7-zip's benchmark, it seems to like it doesn't actually do what the compression workload does, and it also executes for what seems to be a fixed time rather than a fixed instruction count. So this is a better look at what the difference actually is. And I'm running this through tools like perf for my own tools, and simply using CPU performance counters to see how many instructions have been executed. If we look at other CPUs here, I think this one was like 17 megabytes per second. This ran at like much less. This is like 14 megabytes per second. And this is also not fair to IBM. I think this was 12-ish because IBM Power 9 is actually a 32 thread. If you look at 4 cores, you're actually 32 threads because it's 8-way SMT, and if you load up all 8 threads, this suddenly starts annihilating everyone. But that's besides the point. It's going to go at like nearly 70 megabytes per second. Anyway, the point here is that there's not a very big difference in instruction count, and we are making trade-offs for it. And earlier I said there was going to be a trade-off in instruction length because of the extra prefixes. That's going to be hard to gauge, again, because we don't have any tools that can actually compile to APX right now. But what we can do is we can go through existing code that does use REX prefixes, that does use EVEX prefixes, because AVX 512, remember, this thing uses the EVX prefix. And then if you run existing code in either compile for 32-bit or 64-bit, 64-bit can use the REX prefix. And you can start to see the effect on instruction length. Here I'm actually not using performance counters. I am running programs through Intel's software development emulator. It emulates a CPU. And what it can do, because it's not an actual CPU, is it can give you very detailed reports on the executed instruction stream. So it can count every instruction that was executed that has 1 byte length, 2 byte length, so on. And what we can see here is with AVX 512 and the EVEX thing, you end up having rather long instructions. This is 6 bytes. That's probably the 4-byte EVEX, plus an opcode, plus a mod RM. That's 6, right? And then you have a few longer ones. Maybe you have a SIB byte. Maybe, I'm not sure what the case is. But in any case, once you use these EVEX prefixes in YCruncher, which uses a lot of AVX 512 code, then your instruction length tends to increase. And we can see the same effect when x86 transitioned from 32-bit to 64-bit. So when they added the 1 byte REX prefix, before they did that, a lot of, well, not most of instructions, but a plurality of instructions had a 2 byte length. That's probably an opcode and a mod RM byte. Once you add the REX prefix, a lot of those shifted to becoming 3 bytes. And similarly, any instruction that was 3 bytes before you put a REX prefix on, it becomes 4 bytes. So there was a small increase in average instruction length. That's not a good thing, but there are mitigating factors. So there is an op cache on most modern x86 CPUs. And what that basically does is your fetch width does not depend on your instruction length. If you fetch from the L1 instruction cache, you can actually run out of instruction cache bandwidth, particularly on Intel CPUs that support AVX 512 that have 16 byte per cycle instruction fetch. Because if you start spamming instructions that are like really long, then you run out of instruction fetch bandwidth from L1I. But the op cache, well, what matters is just how many ops are fetching from it per cycle, and that's a huge number. On like Golden Cove and Zen can both do 8 per cycle. It's pretty ridiculous. So as long as you fit into op cache, it's not a problem. In recent generations, Intel has also gotten to 32 bytes per cycle for instruction cache fetch. AMD had actually done the same many, many years ago in like Athlon, like 64-bit Athlon, when they supported, actually that's Athlon 2, when they supported 120-bit SSD. So you're not likely to have any instruction cache bandwidth issues either. Where you will have an issue is possibly when fetching from L2. So that is basically when you have a large instruction footprint. So compilers are going to have to make a decision here. Should I use these REX2 and EVEX prefixes to get these benefits that could give me a small decrease in instruction count, but potentially reduce my IPC because if it spills out of L1I, then I have less instruction cache, I have less instruction fetch bandwidth from L2. Another thing is these extra instructions like JMPABS or those conditional instructions. Those could also decrease instruction count. Potentially in some cases they could give you a large reduction in instruction count. anticipate those cases are probably going to be rare. You're probably going to cut it down by a very small amount, and it's going to be a minor latency benefit, because instead of like saying putting a branch ahead of like a C move, because the C move might fault and you want to avoid that, you can save an instruction there. What it's not going to be like is it's not going to be like some specialized vector instruction set. It's not going to give you some massive 50% or 2x improvement in specific applications that use it, like linpack. It's likely to give you a very small improvement across a lot of integer code, assuming the compiler has been updated to use it, you have a new program, or you're using code that's been recompiled to take advantage of these things. That's another thing. This is not going to be an automatic benefit that you see on existing programs. And in terms of hardware, will this save costs in hardware? I don't know. But the one thing is that the suppression of flags output is probably meant to save some hardware. So if you look at ARM CPUs, they have far fewer renamed registers for flags because they only use flags for compare and test and a few other specific cases. So they don't expect most instructions to actually write flags. So for like, let's say you have 96 integer registers, they may only have 25 flags that they can rename to. A lot of x86 CPUs, in contrast, will rename flags right alongside the integer registers. So, for example, you can see this is actually a die shot from Frisch and Fritz. This is Cannon Lake. You can see that there is a lot of die area taken up by, like, these are vector execution units. So this is AVX 512. Well, not actually with the 512-bit extension, but this is 256-bit AVX. You have the 512-bit vector register files. You have the mask register files. You have the integer register file, and then you have the renamed flags right alongside the integer register file. Now, Intel actually keeps as many flags as their integer registers, because so many x86 instructions write to integer registers and the flags at the same time that it makes sense to rename them together. AMD has recently separated them. Intel may be looking to do the same, but you can start to see the issue with this. You can see how much area is in the register files. You can see how much area is in execution units. And really, shrinking this thing, that's going to buy you something, but it's not going to buy you a whole lot. So I don't really see a huge benefit from this, especially if they have to maintain this larger flags register file to make sure legacy code performs well. It's going to take a lot of time to actually transition and migrate and use a new instruction set extension like APX. So what does this all mean? APX, the high-level thing is that it's going to reduce the instruction count at the cost of extending the instruction length. So the instructions that were nominally 3 bytes before may turn into 4 or 5 or 6 byte instructions. It trades speculative register file capacity for architectural capacity. It may reduce the flags register file a few generations in the future. And putting all of that together, assuming all of this is used, you have the compiler infrastructure in place to take care of this. You have code that's compiled for it, and so on. It's probably going to be a net win. It's probably going to be a very tiny one. I will be really surprised if you get even like a 5% gain out of APX. Like if you took a CPU architecture today, gave APX support, compiled code with like compiler knowledge of these APX features, yeah, maybe 5% would even be stretching it, simply because of all the optimizations we have around move elimination, around zero-latency store forwarding. So yeah, it's going to be a cool update for x86, no doubt. I think it's going to be cool, especially for assembly programmers who are going to be able to use these features. It's going to be cool for compilers too. I mean, it's going to make some of the register allocation a little bit easier for them. They can avoid spilling more often. But in terms of performance, it's not going to be a big deal.